Okay, guys, it's 6:40. So getting started. Simon, I don't know if you want to introduce
Yeah,
me or anything, or
uh,
like.
sure. Yeah, we can start this off. So Daniel is I kind of give his background in the email already. He's a master student, finishing up his degree this fall, actually. This spring. You're graduating soon, right?
Yeah, I'm writing this.
Yeah. So he's in the School of Information doing his master. He's very knowledgeable on this topic of blockchain analytics. So we're really lucky to have him today. Yeah.
Cool, awesome. Thanks, Simon. Yeah, note that I needed a formal introduction since I didn't know how you guys kick things off. So hi everybody. So yeah, I've been part of Blockchain Berkeley for the last over a year and a half. I'm very interested in performing data analysis and beyond that, I'm very interested in kind of like studying and understanding social technical systems and how they emerge and how people interact with technology in general. So that's why I've been looking into different topics around blockchain and using network analysis to understand different phenomena within the space. I've done research in Bitcoin privacy, looking at how deterministic wallets have been adopted. I've also done research on Ethereum mining and relationships between miners. Actually, the homework or the demo we'll be looking at today is kind of related to the topic. And currently, I'm doing research on the Lightning Network, and in particular, on like the strategic motives and intentions behind public node operators in the Lightning Network. Sort of like looking at what are the incentives and how those incentives kind of like drive the stability of the infrastructure and the network in general. So if you're interested in data analysis and in the space in particular, hit me up and I'd be happy to like chat a little bit more about my research. So this session, basically, I just wanted to share with you like three things that I think are kind of like interesting and relevant when you're sort of like working with blockchain. I know this is developer DeCal, but I'm assuming that some of you, I don't know if most of you took like the fundamentals DeCal. I think it's taught in the fall. So maybe some of this is already sort of like stuff you know either from this DeCal, the previous DeCal, or just like because of life. But I think there's some interesting nuggets in sort of like looking at what blockchain data can tell us. And in particular, when I sort of like came into the space like a year and a half ago, I was missing kind of like a reference or a resource that would give me some context in terms of like where is sort of like the blockchain ecosystem standing in comparison to like the financial system in general, maybe like other technologies, etc. So this is just going to be like a data dump. I'm just going to give you sort of like a lot of like data points around the what's happening in the space, in particular around like sort of like answering these three questions, like what is blockchain, how can you think of like blockchain, like who is using blockchain, and also like that other question of like how is blockchain technology being used. And then for like the second, third and fourth parts for like the rest of the lecture, we'll be looking more sort of like in depth and in detail into sort of like accessing blockchain data and working with blockchain data. So I'll be going through some of like the most popular online explorers. Probably some of them you have already seen, but there are others that you might have not, which are more niche and have some like interesting data sets. Then we'll be looking at how to like get an extractor of data. So like through the semester, so like the last few semesters, I've explored different data sets and I found interesting places to get like quality structured data to do like research and analysis of blockchain data. And then we'll be working on so like a little bit of theory around network analysis, graph analysis. So again, some of you, if you have taken like a network analysis course, and even I know that some of like the introductory CS courses um, do some like graph theory and network analysis. So we'll do some graph theory, just like the fundamentals and the basics, so that we can move on to like the homework. We're going to do it more of a like a demo workshop kind of thing, where I'll be just going through the notebook and showing you how to analyze a specific data set we have for today. And in the process, we'll be just exploring some one specific network analysis library, but I'll also point you to like other libraries that are pretty common and pretty used in research around network analysis. So that's a plan for today. Hopefully we'll be under the 2-hour mark, maybe like an hour and a half. I know that staring at a screen for a long time is not the best way to do this, but hopefully work out. And I have a 6-month-old baby who's teething, so you might hear him scream every now and then. So sorry about that. So let's get started. So I just want to have like this initial overview of, let me just put a timer here so that we stay on time. So I just wanted to have like this initial this initial overview of relevant like data, ways in which we can describe blockchain from a data perspective. So this is a list of the top 100 cryptocurrencies by market capitalization. The total market capitalization as of today of like those 100 cryptocurrencies is a little bit over $193 billion. You can see that Bitcoin and Ethereum are the top 2 cryptocurrencies by market capitalization, and that's like over 73% of the market cap of all cryptocurrencies. So if you compare that to, say, like the Nasdaq 100, which is the index of like the 100 like most valuable technology companies, the value of that index and the market capitalization of that index is around 9.6 trillion as of today. So you can see just this gives you some perspective of how big is kind of like the ecosystem and, you know, like crypto assets as a new asset class in comparison to like other asset classes. When you're thinking about defining blockchain, like the other like common comparison is thinking of blockchain technology as a payment technology, as a payment network technology. And this is a pretty interesting graph. Is updated. I think this is December 2019, and it shows the total number of transactions for different blockchains. Of course, again, you have Ethereum and Bitcoin as the blockchains that are processing most of the transactions in the space. But if you add up all of the transactions that have been done across blockchains over time, they add up to 3.1 billion transactions. Something interesting is that 2019 has a third of those transactions, 1.1 billion. But again, if you compare the number of transactions like done in 2019 in different blockchains, which is 1.1 billion, to the daily transactions that Visa processes, for example, you see that sort of like the adoption of the technology is still sort of like lagging, and you could question
Daniel,
to what extent.
Sorry.
Yeah.
We can't see your screen share.
Yeah, I don't think you turned on the screen share.
Oh,
Yeah.
Okay. So you haven't seen any of it?
Yeah, we haven't seen the graph yet.
Yeah, not yet.
Oh, sorry
Yeah.
about that, guys.
Yeah. All right, now we're
can you see it
seeing
now? Okay,
Yeah.
sorry about
Yeah.
that. Okay, yeah.
Yeah, no worries.
Oh yeah, you should have told me before. Yeah. So this is what I was telling you before. This is the market cap, 193 billion as of today, and this is Nasdaq 100, 9.6 trillion. And I was just showing you this graph. This is aggregate transactions in blockchain in the last 10 years. Of course, like in the last few years, it has grown a lot, but still, it's way behind kind of like the transaction volume that you have for other like payment networks like Visa. Another way to think about blockchain, what blockchain is you can think about it as a computer network, a distributed database, and in particular, like you want to think like and understand how many people and how many nodes exist in that sort of like that computer network. So here is the difficulty, like the total hash rate in the Ethereum network. This is in gigahashes per second since the start of the network. And this is kind of like the same graph that for Bitcoin. You can see that obviously because of the way Bitcoin mining happens, you have like more difficult hashes and nonces that should be solved for. So this is in terahashes per second. And on average, it has been estimated that there's probably like 1 million independent miners for Bitcoin and 250,000 independent miners for Ethereum. Of course, you probably talked about this in previous sessions, but mining in both Bitcoin and Ethereum not only has so like centralized or become highly centralized in the past few years, but it has also changed in the way it's structured. So you have like these big mining pools to which like folks contribute computing resources. So this is a difficult number of estimate, but that's another way you can think of blockchain, which is this collection of people that are running different implementations of specific protocols. So this is another way to look at it. Yet another way to think about what blockchain is this gargantuan energy consumption machine. So these are some interesting stats about kind of like Bitcoin usage of resources across time. So if you look at like the annualized total footprints for Bitcoin in terms of like its carbon footprint in a year, Bitcoin is equivalent to the carbon footprint of a country as Denmark. This is like a very common number that gets thrown around a lot, which is the total electrical energy consumption. So Bitcoin, validating Bitcoin transactions consumes the same amount of energy as the amount consumed by Austria. And then you have, the amount of electronic waste is equivalent to the one produced by Luxembourg. And if you look at single transactions, sorry about that. If you look at single transactions, you can see that validating one Bitcoin transaction is equivalent to validating 862,000 Visa transactions. And again, in terms of like electrical energy, validating one transaction is the equivalent of energy that's needed to power like a US household for 24 days. So this is another way to look at what blockchain is, and this is like from the data perspective, what the data can tell us about what blockchain technology is. So another relevant question is like, who uses Bitcoin? What is this technology enabling, and who's benefiting from whatever the technology is enabling? So if we look at Bitcoin active addresses, that's the amount of addresses that have, that in the case of Bitcoin, that have sort of like unspent transactions associated to them. And in the case of like Ethereum, where you have more like an account-based model, is the addresses that have positive balance. You see that, of course, this grew significantly. This x-axis is not on the same scale because this is since the beginning of Bitcoin. This is since the beginning of Ethereum, which started in 2015, and Bitcoin started in 2009. But you can see that there's this peak during like the bubble, late 2017, early 2018, where like these technologies became really popular. But then you see that coming down and sort of like stabilizing for the last year or more around 379,000 active addresses for Ethereum and 600,000 addresses for Bitcoin. And again, if you compare this to like other like relevant statistics about digital currencies and digital payments, you see there was a survey that was done earlier this year that estimated that by 2019 there were like 36 million US crypto holders, like people that held some kind of cryptocurrency. So what you can see that's interesting is that not necessarily every person that owns cryptocurrency interacts with it directly through the blockchain. A lot of people simply trade and buy cryptocurrencies through centralized exchanges. So you see that the technology itself has sort of like become an underlying almost like settlement layer that powers exchanges that people use to sort of like transact and buy these assets. And then if you compare sort of like this volume in terms of accounts and also like crypto holders to say like the number of customers that JP Morgan Chase has on like their digital platforms. It's 51 million for 2019. And if you compare that to say like PayPal active users, that was over 300 million for 2019. So this gives us some context as to like who is using the technology and like how are they using it. And then something that's really interesting, going back to that point of uh, how is the ownership of 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 cryptocurrencies sort of like distributed, and furthermore, like how is the custody of cryptocurrencies sort of like being managed, and how does that space work? So you see this is the distribution of coins, and sort of like the balance by number of addresses. So basically what's really interesting here is that you can see that uh, less than 3% of Bitcoin addresses hold over 95% of the total like Bitcoins in circulation. So you see there's a huge centralization of ownership in Bitcoin. The stats are sort of like very similar for Ethereum. But what you see there is not only the fact that obviously you have a lot of like probably wealthy individuals or institutions that sort of like hold a lot of Bitcoin, but also that you have these centralizing entities, in particular exchanges or other custodial services that hold most of the crypto assets in circulation. So what has been interesting, sort of like around the exploration of data and performing data analysis with blockchain data is sort of like understanding who these users are. So this is kind of like taking us to like almost like the type of data analysis and methods that are commonly used in exploring blockchain data. But the most common kind of like clustering heuristic to identify individuals in blockchain data, in particular in Bitcoin, is sort of like looking at common inputs to a transaction. So I don't know if you've heard of it. That already happened a few years ago. But by basically doing like using some of these heuristics and performing community detection, that's how the famous dark web market, Silk Road, sort of like got persecuted, and they were able to find the people sort of like behind this market, where they would sell anything from like guns to drugs to whatever, and most of the payment happened with Bitcoin. So by using common sort of like address input clustering heuristics, they were able to track people behind this market. And also, I don't know if you remember, this was also kind of like a big thing a few years ago, when it was all the ransomware attacks that were happening around the world. So they would basically lock people's files, and they would request a ransom to unlock them. And many of those operations kind of like requested the ransom payment in Bitcoin. So again, a lot of forensic work has been performed around sort of like transaction data to sort of like identify people that are sort of like misusing the technology, both for sort of like selling illegal items, like hacking others, and also there's a lot of kind of like money laundering that's happening on chain. So that application of like following the money trail in order to like identify bad actors has been an interesting and relevant one. Again, to the question of like who uses blockchain, another interesting sort of like data application that has been growing in the last few years, and if you're interested in sort of like working on this and want to like look at more literature, I'd be happy to share more literature about it. But there's the idea of like understanding the financial fingerprint for different individuals, institutions, or services in blockchain. So kind of the way it works is that as sort of like as you have like many biometric markers, say like your fingerprint, your iris, even kind of like the tone of your voice or whatever, many folks have had sort of like the hypothesis that different kinds of services um, in blockchain transaction networks. Most of this work has been done in particular in the Bitcoin transaction network, but there's some interesting work in Ethereum as well. But what they argue is that these entities have specific transaction patterns. So the transaction patterns sort of like relate to what's called in network analysis and in graph analysis, kind of like their graph motifs. So a motif is kind of like a subgraph, like a subset of a graph, and so like the nodes and edges in a graph and how they relate to each other. So there's been some interesting work that basically uses machine learning and a bunch of like graph attributes to sort of like classify different kinds of entities in different blockchains, and in the Bitcoin blockchain in particular, as different kinds of services. So there's this work by Jordan in 2018 where they basically had they used a random forest and they used a bunch of features. They used like over 300 features to sort of like categorize different entities in the Bitcoin blockchain. And they sort of like were able to divide them in different categories. So this graph is actually from a different paper, but that uses a similar technique. This is from Zirui in 2017. And basically like they end up classifying the like a big set of addresses in the Bitcoin blockchain. And as you can see, like a big chunk of those are attributed to just like personal wallets. But then you see another big chunk is exchanges. You have gambling services as a big part of it. But you also have like non-negligible size for like ransomware, sort of like scams or like dark markets, or like other types of addresses that are associated with legal activity. So kind of like analyzing the topology and specific characteristics of different entities within the transaction graph has been and has proven to be useful to sort of like characterize and de-anonymize many of those entities. So moving forward to like another interesting or relevant question in the space, and it's like, how is blockchain used? This is an interesting graph from work that was done by Carter in 2018. And basically what they did is they looked at the Bitcoin Talk forum and they categorized posts manually. So this is kind of like a mix of qualitative and quantitative work, but they were trying to understand how are people thinking of the technology, and you can clearly see the change in sort of like the way people conceive this technology. At the very early sort of like days, most of the conversation revolved around thinking of blockchain and of Bitcoin in particular as an electronic cash, or as a sort of like payments network. You can see that it's probably like over 80% of like the participants in these forums were thinking of the technology as having that potential to like become these electronic form of payment. But as time evolves, like these two uses lost a lot of sort of like relevance in the community, and towards like 2018, you can see that the most sort of like discussed use or application for the technology was more like a censorship resistant e-gold. So again, you've probably heard these terms thrown around, the idea of like blockchain and Bitcoin in particular being a store of value, or being a medium of exchange, etc. So it seems like sort of like a safe haven asset or a store of value has become the most pervasive kind of like thing to understand the technology. So what's interesting is looking at the data and seeing what uses, like by looking at the data, how can you sort of like infer the way in which people are using the technology or using these assets. So this is an interesting paper by Fry in 2018 that sort of like performs some statistical tests using like financial models to determine to what extent you can say that there are pricing bubbles happening in different cryptocurrencies. In particular, they look at 4 cryptocurrencies: Bitcoin, Ethereum, Ripple, and Bitcoin Cash. And they find, at least up to mid-late 2018, that there is evidence for bubbles or the existence of bubbles in Bitcoin and Ethereum in particular. So again, it's interesting by looking at the pricing mechanisms, not only, and sort of like the pricing dynamics and pricing data, which is not strictly related to data that you see on the blockchain. A lot of pricing, and sort of like a lot of transactions happen off chain with centralized providers, but still, if you look at the pricing dynamics, you can say things about the way in which the technology is being used. So again, this is something that a lot of people kind of like hypothesize that's the case, that most of the action that's happening with cryptocurrencies is about just speculation, and there's no like real use case behind it. So this is an interesting kind of like application that shows to what extent that's the case with Bitcoin and Ethereum. Another kind of like application for cryptocurrencies, and another application sort of like and another kind of like perspective that the data provides is understanding to what extent blockchain technology is being used for payments, for like regular payments. So I believe that you've covered the Lightning Network a little bit in previous sessions. The Lightning Network is basically a solution that sort of like expects to make Bitcoin transactions faster and cheaper. And the idea behind the Lightning Network is to enable micropayments using Bitcoin. So the Lightning Network has been out for like almost 2 years. It got launched in like January or February of 2018, I think. And this is the second largest node operator in the Lightning Network. It's called OpenNode. And basically they have a bunch of nodes and they route payments, and they just accrue fees from routing payments. So this is relatively recent data from a month ago that shows the number of transactions, and in particular of payments, that they have routed through the nodes across kind of like the last 6 months or so. And as you can see, like the amount of payments being routed through the network to like their nodes, which probably constitute I'd say like over 20% of like their routing nodes in the network, is still relatively low. So here at the peak in February 2020, in terms of like volume routed of like, this is in Satoshis. So that's 120 million Satoshis, which is roughly $10,000 in volume. And in terms of events or like payments routed, you see that it's under 200 events daily. So again, if we think of that number of Visa processing 100 million transactions per day, so you can sort of like see what picture the data is painting in terms of like how much adoption has the technology received with respect to payments. Another kind of like interesting perspective that's brought by the data, it's kind of like looking at smart contracts in particular in Ethereum that have been used for initial coin offerings. So I know that ICO acronym doesn't say a thing today, but it was very popular a couple of years ago, and you see that they were there were months in early 2018 where there were companies, I mean, the whole market was moving around 1.6 billion in dollars, kind of like fundraised through ICOs. So it was like a huge application for Ethereum tokens in particular, this idea of like tokenizing securities and creating digital securities that would sort of like remove the middlemen in sort of like the process of helping companies get funding, right? So there was really big, that there was a huge application of Ethereum and smart contracts in particular, but that almost like completely dried out by early last year, and it's almost like non-existent this year. So this is another kind of like interesting and relevant data point about like how is blockchain currently being used. This is a hot topic now, and I don't know how hot it still is. It was at least pretty hot late last year and maybe early this year, but this idea of like decentralized finance. So most of like the applications in decentralized finance, again, are happening with smart contracts in Ethereum, services like Maker or Compound that allow people to basically lend their crypto assets, and they can sort of like guarantee that they're going to be paid back because the loans that they make are over collateralized, meaning that people have to put forward a lot more money than the one they're actually lending. So you can see the sorry about that. You can see the number, the value that's locked in DeFi contracts. This is like across time, and in particular right now, it is obviously this is probably COVID in sort of like in the last like 3 or 4 weeks, but the current value locked in DeFi contracts is around 690 million. You have like one big player that's MakerDAO that has almost like 50% of that market, that offers kind of like lending services. And at its peak, like a month ago, it was around like 1.25 billion. But still, if you look sort of like an equivalent market in like the real world, the U.S. bond market, and this is a bit outdated, but still, this has actually grown a lot. Especially corporate debt has grown a lot in the last 2 or 3 years. But if you look at the bond market, you see that the bond market is over $39 trillion. Like if you count like different kinds of bonds, and in particular, if you just look at corporate debt, that's over $8 trillion. So you see that like these services and these applications have sort of like gained some interesting traction, but it's always interesting to kind of like have that context and compare them with sort of like the real world alternative. So what I like about looking at data and exploring data is that it gives you the context of like what's happening in the space. And I don't know like what your interests, why you guys interested in the space. I don't know if you're looking at launching a product, or you have a project related to the space, or if you just want to learn a little bit more about it, or just intrigued about like how these mechanisms and sort of like we like to call them in the iSchool, social technical systems emerge. But still being able to leverage data and use data to sort of like better analyze those interactions is pretty valuable. So now I just wanted to like go into like a more sort of like applied part of like the lecture, and take you guys through some tools and services that might be very useful in kind of like the process of gathering data and exploring and playing a little bit with data. So let me just pop out of the presentation mode so we can like visit some of these explorers. So basically, you have a lot of online explorers and online dashboards and data services that are pretty useful for just like browsing and looking at data. So the first two, the blockchain.com and etherscan.io, are your traditional sort of like explorers, where you have the ability to simply just like browse specific, sorry about that. The ability to just like browse specific transactions, specific block or address information, but you can also have dashboards that give you interesting or relevant information about, for example, um, mining dynamics, or even like network activity, or market activity, which is pretty interesting. Um, Etherscan does, again, it's an online um, uh, blockchain explorer. So again, you can look at specific blocks that have been mined. You can see who mined them. You can look at the individual transaction addresses. I'm pretty sure you're familiar with like these services. Um, but you can also look at uh, like their charts and general statistics of the network. So again, they have market data, they have data about sort of like the blockchain, they have data about the network. So that's pretty interesting. So those two are pretty standard and pretty common. I'm sure you've already seen them. Then there's, I think I actually did not include this one in the list. I'll make sure to include it. But there's this bit info charts, which is kind of equivalent to Blockchain Explorer and Etherscan IO, but it offers information for a wide variety of, of, of tokens and crypto assets. And something that's pretty interesting is that it sort of like offers some other kind of like information that's not standard and that you don't regularly get in like traditional explorers. So say like for Bitcoin, it shows you, okay, like the blockchain size, but it also shows you information about their client implementation. So you have the latest release, you have the latest commit, stats like GitHub starts. They also show you like chatter about that asset in social media. So you have like different tweets per day, and you have that for different currencies, also like Reddit subscribers. So again, if you're interested in sort of like looking at the data angle, if you're interested in exploring data, that kind of like parallel data, aside from like the traditional sort of like transaction data you can get from the blockchain, it's very relevant and useful. And another kind of like service that has popped up in the last few years is TXStats. This started like a community project from the one of the engineers over at Coinmetrics, but it has now become like a partnership between Coinmetrics and BitMEX, I think. So now you have like more specific and technical sort of like dashboards and data for, let's say, Bitcoin and the Lightning Network. So for example, you have so like pay to script statistics, which is interesting. So I think you went over like Bitcoin scripts last week with Akash, but this is sort of like showing addresses that have sort of like pay to script UTXOs, and it gives you information about those UTXOs, the number of UTXOs, the volume of Bitcoin stored in those UTXOs, and dynamics over time. So it's a little bit more specialized with respect to like the type of statistics you can get. Also here, like it has statistics about fees, etc. So this one's pretty useful and interesting. Some of these have API services, so you can download some of this data, so you can play around with it. Later in the lecture, I'll show you like the couple of like the services I use to download data. But I'm sure like these services that have some like process data allow you to download that process data as well. Another service that's kind of like interesting and different is Sentiment. So Sentiment, again, it's similar to what Bit info charts sort of like offers. But what these guys do is, again, they create like these dashboards with a lot of information about specific assets. So they have, again, like social information, market information. They have like on-chain information. In the case of like Ethereum, etc., they have information about specific tokens. So this is pretty cool. It's probably very similar to some private high-end services that exchanges and institutional investors use. But it gives you a lot of details and insights into what's happening in the space. And then you have some more like specific kind of like dashboard and online data explorers. There's this DeFi Pulse data explorer. That's actually the one I used to show you the DeFi data. It kind of like goes and shows you like different DeFi contracts, from decentralized exchanges to lending platforms to derivative platforms, kind of like their market activity, their locked assets, etc. So this was pretty basic. That's like very specific to like the DeFi sort of like space and understanding the DeFi space. This one is kind of interesting because I know you guys have been working and a significant part of like this developer DeCal deals with applications in Ethereum and Solidity, and you have this is kind of like a Ethereum application tracker. So it gives you kind of like these graphs of like what other accounts are associated with your application, with your contract. So it's interesting. Again, it's more geared towards smart contracts in Ethereum to like ERC20 tokens, etc. But it's interesting. You can get information from them. It seems like they have the API. This other dashboard, 1ML, is kind of like the equivalent of blockchain .info or .com or Etherscan, but for the Lightning Network. So the 1ML kind of like offers you information about specific nodes, the specific channels, the specific capacity locked into those channels, and kind of like the dynamics of the network. So again, as I was saying, you can see here is async. There's OpenNode, which was the company I was telling you about. So you can have like all the information about their public nodes and their activity. Obviously, in the case of the Lightning Network, all transactions are private, so we cannot really see them. But you can see things like when were like new channels created, what's the capacity for those new channels, when were new channels closed, etc. And you get like some tags and information related to each of the channels. So again, if you're doing research or you're thinking of launching a Lightning wallet or stuff like that, this might be a relevant kind of like source of information. And then you have some other services that are kind of like paid services that are mostly used by exchanges and institutional investors and even regulators. So there's coin metrics, there's chain analysis, and there's Kaiko, and I don't know if there's people here in the room that is interesting. That like this one, Kaiko, I found really interesting because it offers like one of the challenges when you're doing research with blockchain data is that in particular, if you want to look at like financial aspects and trading aspects, a lot of trading happens off chain. It happens within like decentralized exchanges. So if you want to look at the dynamics of trading and how that's playing out within like not decentralized exchanges, but just exchanges in general, and how that trading is happening within like exchanges, you're not able to access that data. The data is mostly private. So Kaiko is basically a service that offers, they sell you private exchange data. So if you're, I don't know, like working on a project or part of so like research initiative or grant, you could sort of like look into the data, which is interesting. So this is kind of like the online explorers and online services. But other sources of data, more like if you just want to access raw data, is like one, you can just like run a node and try to like parse the blockchain data itself. But I like definitely don't recommend doing that. That's super cumbersome, and you'll spend more time just wrangling with setting things up and then like figuring out how to parse the data. So there are like three sources of data that I found pretty useful and pretty convenient. So these guys, these are guys from CS over at Princeton, the BlockSci guys, they have an awesome analysis library for Bitcoin. So let me just show you that. I think I opened that over here. So what they have, which is pretty interesting, is just move this over here. Is they have like you store the thing with them is that you have to like you need a machine that's sort of like big enough storage wise and memory wise, because they basically load the whole Bitcoin blockchain on memory. So they have like a very efficient way of kind of like having that in memory blockchain database, and they provide an analysis library that makes it really easy to sort of like work with objects and elements within the Bitcoin blockchain. They used to have an image for Amazon Elastic Cloud. I used that for some of my research, but just working on this presentation, I saw that a couple of months ago they took that down. So you have to like work on the setup yourself, but they're probably getting that back up soon. So so basically they allow you to do things like so you just initiate a blockchain object. This is like the actual Bitcoin blockchain that's syncing on your machine, and you can just have this blockchain object that has like a bunch of like methods. You can just count addresses, generate all the blocks from the blockchain object, get all the transactions for the blockchain object. So you just do like blockchain.blocks.transactions, then you can get like all of the information and you can manipulate it in memory. So yeah, or again, you have a transaction class and you can just read attributes from that transaction class, you know, like the block number, the block height, block time, etc. So when you're doing data manipulation, this is a Python library. It's super convenient because you just have the data there in memory, and it can be really helpful to just like create a complex analysis around transaction data. Another source of like good data for multiple blockchains is Google BigQuery launched, you know, they have like their public data sets. So they launched, I have that over here. They have launched a bunch of like structured data sets for different cryptocurrencies. So you can, let me just reload that. You can access structured data sets for Bitcoin, for Ethereum. I think they have Litecoin. I think they have things like Ethereum Classic. I think they even have like Dogecoin or stuff like that. So the cool thing is that they've just like parsed all the blockchain data and they just created a structured version of it. So you can just run SQL queries against it, and you can use their yeah, I think I have too many tabs open. You can maybe try and come back to that one later. But basically, you can just run SQL queries and pull data again for like blocks, for transactions, for Ethereum. They have like underlying like network as, I mean, like not the transaction network, but the actual miner network. So you can have sort of like data about transactions that are in the mempool, communication between nodes in the network, which is pretty interesting. We can come to that back later. So that one's a pretty good resource, and again, you might need Google or GCP credits to use that one, but I know there are like free student credits available, so that's a useful thing. And then there's for the Lightning Network, there's this company that's actually, I think they have like a wallet in Asia or something like that, Big Sun. I actually hadn't heard about them before I started playing with like Lightning data, but they have, so they actually have a block explorer. Just go ahead and kill it before it kills us. Okay. So they actually have a block, like a Lightning explorer, which is pretty neat. It's kind of useful if you just want to have an overview of what's happening in the network. So again, it shows you historic information about node openings, node closures. There we go. So it shows you the capacity of different channels, the number of like openings you've had, closings you've had on a daily basis, the types of channels that are so like opened in the network, and the reason why kind of like channels have been closed. So you can see like if they were closed but because they were like they were forced because the channel was not being used, or there was just a mutual closure, etc. So this is kind of useful. It also shows you information about big nodes in the network and their amount of channels. But more than that, what's interesting is that they have an API. They actually used to have like just the SQL data on their site to download, but I think they just change that to like an API that just returns JSON data structure. So like you can just use their API to like get a list of channels and all the channel attributes, get a list of nodes, get a list of policies that different channels have different p-policies. So that's kind of like an interesting data source if you're looking to research and work with lighting data. Actually, the lighting research I'm conducting right now is using data from their API, and it's pretty good and pretty reliable. So I just wanted to, for the next maybe 10 minutes, hopefully this is not too dry, but I just wanted to give like a very short primer on blockchain, on graph analysis and network analysis. So this might be just a review for most of you guys, but hopefully it's new for some of you. So again, I borrowed most of the slides from I think it's CS 224 over at the Red School. Sorry for that, but that doesn't seem to be like a network analysis, like a comprehensive network analysis or standalone network analysis course at Berkeley. I don't know what that's the case, but just get back to presentation mode. Probably that'll take us like 10 minutes, that we can get a break and go back to working on the notebook. So just give me a second. I'm going to turn on the lights here. I'm sorry. Okay, I think recording this session is starting to be too much for my computer, so hopefully this doesn't die. So if, I mean, you're obviously all probably familiar with graphs. But you know, like there's actually like a formal way of defining a graph, and it's basically a collection of vertices or nodes, and a collection of edges. So in this kind of like toy example, we have a graph that's defined by 8 nodes, 8 vertices, and the following edges. This is actually a list of edges. So you can think of edges as either, and if we're thinking about it kind of like in programming terms, you can think of them as either sets. In the case of like undirected graphs, so this is an example of an undirected graph because each of the, like none of the edges has like a direction pointing either way. So it's a set. So like having the set v1, v2 is the same as having the set v2, v1, like the order doesn't matter. But you can also think about those edges as tuples, right? And you can have like order tuples, and the order of the tuple so like tells you which way is kind of like the edge pointing at, and how is the relationship established. So if you have a directed graph, that means that you have directed edges. And a non-directed graph, it means that you have undirected edges. So they can just be formally thought of as sets. And in addition to that, when you're defining a graph, you can think of the nodes. You can assign weights to the nodes, like specific attributes to the nodes, and you can also assign specific attributes to the edges, right? So, for example, in the case of blockchain transaction data, what's the most kind of like common way of modeling blockchain transaction data is to assume that each address is a node, and then you create an edge between two addresses if there is a transaction between them, right? So you can create kind of like a what's called like a multi-digraph, which is a directed graph that can potentially have multiple edges between two nodes. So that would be kind of like the most common way of modeling transaction data in blockchain, because you can have potentially more than one directed edge between two nodes. But many times what happens, and that's kind of what we will be doing in our workshop, what you do is you collapse all of like the different edges into one edge for each one of the directions. So let's say you have 10 transactions between V8 and V5, and each of those transactions is one Bitcoin. You can choose to model it as a graph that only has one edge, where the weight of that edge is 10 Bitcoins. It's kind of like collapsing all of those transactions into one edge. And that's basically done because a lot of like the kind of like algorithms that are used to calculate network properties are a lot more efficient if you run them or on like simple directed graphs or simple undirected graphs. So this is kind of like formally how you think of like defining a graph. And of course, you can already see like why using graphs and network analysis is very relevant in kind of like the context of blockchain data. And then kind of like what's sort of like relevant when you're analyzing blockchain data is kind of like measuring these graph properties, these network properties. So the kind of like one of the most common properties that you analyze when you look at the network is kind of like the what's called the degree distribution. So the degree distribution is you want to see kind of like what's the probability of a randomly chosen node to have a degree k, and the degree of a node is basically the amount of edges that it has, the amount of like other nodes that it's connected to. So if you have a directed graph, you can think of like in degrees and out degrees, meaning like edges either like pointing out or pointing inwards. Or if your graph is undirected, like this one in this example right here, you can just think about the degree as the number of edges connected to that graph. So you want to look at the distribution of degrees for your graph. So you want to look at on average and how many sort of like edges are connected to each one of your nodes, and how are those edges distributed across all of your nodes, right? Normally, those sort of like distributions and degree distributions follow a power law. So are you finding complex networks, as is the case of like blockchain transaction networks, is that you have very few nodes that have a very high degree, and a lot of nodes that have sort of like a very small degree. So again, in like Bitcoin transaction networks, when you end up finding is like kind of like, remember as we saw earlier today, you have some addresses that have hold a lot of Bitcoin. So you can expect those addresses to like perform a lot of transactions or have a lot of transactions both coming inwards and outwards. And you will probably have a bunch, like a lot of addresses that are just like change addresses, or even like dust. If you have heard of the term dust in Bitcoin, is just like amounts or addresses that hold amounts that are like too small to be spent, or that's not like economically rational to sort of like spend them, because the value locked in those addresses is less than what you would have to pay for the transaction. So you probably have a lot of addresses that have a very low degree, both inwards and outwards. So degree distribution is something that we want to look at and see like how are nodes connected and how is the distribution of those connections. Another kind of like interesting like property in directed graphs is kind of like looking at the distance, which is basically the shortest path between two nodes, right? So like you want to see in particular in connected graphs or in connected subgraphs of a specific graph, you want to see what's the least amount kind of like of jumps of steps you need to make to move from one graph to another. In the case of, for example, Lightning Network data, understanding the kind of like that attribute and that property is very important because the flow of transactions through the network and obviously the cost of having those transactions routed is directly dependent on how long those shortest paths are. So understanding how well connected are different points in the Lightning Network is super relevant for estimating how efficient is the Lightning Network in comparison to making transactions on chain. And again, in directed graphs, the analogous definition is that basically you don't have that symmetry between the distances because you have edges pointing in specific directions. So when you think of the shortest path, it's obviously the shortest path taking into account the direction of each of the edges. So distance is another like important metric or graph property. Another important metric or graph property is kind of like understanding the clustering coefficient and also kind of like the density or how dense the graph is. So basically you have a way in which you can think about clustering or about density is what percentage of the possible connections between nodes exist in any given kind of like instantiation of a graph. So you have here like for node I, different clustering coefficients where you see kind of like what percentage of the potential edges that the neighbors of I could have are actually present in that specific kind of like version of the graph, right? So if the nodes adjacent to I have no connections between them, like their clustering coefficient is 0. If the nodes neighboring I have like all of the potential connections between them, they have a clustering coefficient of 1. Sorry. And analogous to like the concept of clustering, you have a concept of density, which is almost like taking that concept of clustering to like the whole graph. And you can think of density in terms of like what's what percentage of the total number of connections are present in a given graph. And from there kind of like think of like how well connected the graph is. And finally, we have the idea of connected components. So normally when we're analyzing graph data, we are mostly interested in connected components and in particularly in the largest connected component. So just a connected component is a subset of nodes where you can sort of like go from any point from any node to any other, traversing the existing edges. So like here in this example, we have 3 connected components. One is like kind of like this trivial connected component, which only has 1 node. This one has 2 nodes, and this one has 4 nodes. In the case of directed graphs, where kind of like that direction matters, then you have a stronger kind of like definition, which is kind of like a strongly connected component, which is basically being able, like a connected component is defined as a set of nodes in which you can go from one node to any other, traversing the edges in kind of like their specific direction. So these four measurements are 4 properties, thinking about the degree of each specific node and their distribution across the network, thinking about the distances between nodes and also like the average distance across the network, thinking about the clustering coefficient or the density of a network, and thinking about the largest component and understanding the size of the largest component and the dynamic within the largest component are sort of like the basic graph properties that you want to study and explore where you're looking at complex network data. So again, in the sort of like space of blockchain, most of the data can be thought of as having a graph structure or a network structure. So not only kind of like thinking about miners and the way the network itself is connected, but also at a higher level when you think about the, the network of transactions and how like individual addresses are connected to other addresses via the transactions they have made. And also beyond that, in terms of like maybe mapping kind of like the way in which smart contracts are related in Ethereum, or the way in which routing nodes are related in the Lightning Network, they can all be modeled and thought of as graph or complex networks. So what we will be doing for the second half is basically looking at a notebook that goes through some of the data that I've been working with in the past, and exploring some libraries for network analysis. We will be using the Python library NetworkX for the notebook, but in case you're interested and you want to sort of like play around a bit with like a network analysis library, there are other two like pretty good libraries, Snappy, and that's actually from the same group at Stanford that teaches the complex networks course. And there's also the Spark library for distributed network analysis that's called GraphX, which is that's particularly good for larger complex networks. What I normally do with NetworkX is, because the networks I work with are not that large, but I have a lot of like parallel computation needs, I use NetworkX in conjunction with Dask, which is a library for parallelizing tasks in Python. So we'll go through like a simple version of like initial data exploration of blockchain data for the next segment. So I'm going to stop right here.
Cool. Thanks. I was just wondering what your thoughts were on like the increasing interest in zero knowledge proofs and increased anonymity with blockchain networks, and how you think that'll impact data analysis on chains.
That's a good question. I think that there have been a lot of efforts in like towards sort of like making data more anonymous, and in the process that will eventually make a lot of chains sort of like more difficult to analyze. But I think that I mean there are two things happening there. There's one is the fact that for some types of analysis, like even if you have kind of like encrypted data, you can perform certain types of analysis, and depending on like who's designing the blockchain or whatever, if like they're using homomorphic inscription or whatever, and you can sort of like query and explore and manipulate that data, even if it's encrypted. That will be an interesting trend, and that kind of needs to happen in a way, because, and that connects to my second point, which is that there's an opposing force in the world of like finance and like traditional finance and policy and regulation, that it's exerting a lot of influence in the blockchain phase, and is that you cannot have these like completely anonymous systems if you want to create something that can have mainstream adoption, because you need like KYC, know your customers, or AML, anti-money laundering laws, and that requires you to sort of like disclose or have more structured information. Obviously, eventually you can do some of that stuff using zero knowledge proofs, etc. But you will need to have more structure and maybe more transparency or observability into your data. So I last semester I heard that I guess, and please correct me if I'm wrong, but definitely less than 10% of the Zcash transactions use their like hidden transaction function, their shielded transaction function. And I think it's way less than that. I think it's like less than 5% or something like that. So there's probably also like a user case we made of like why sometimes it's like super cumbersome to have like data super encrypted, but that's a good question.
Cool, thank you. I recently ran into an article that compared chain analysis to like the Palantir of the blockchain space or something crazy like that. And so I was just curious to see where you thought like the ethics of this is going. But I see your point about the necessity and just like preventing these like and like money laundering use cases and stuff like that.
Yeah. Okay, so to give you some context for kind of like the data set that we'll be working with, and this is part of like ongoing research that I'm working on, is one of kind of like the most contentious issues in kind of like the blockchain space is that like people are very concerned about the independence of miners, of validators in the system, and that's particularly problematic and true of like proof of work blockchains, and currently like the two largest blockchains, Ethereum and Bitcoin, are proof of work. I mean, Ethereum is in this process of like transitioning into a proof of stake blockchain, but that's probably going to take a while, and we're probably stuck with proof of work in Bitcoin for a long time. So there's the idea that if you have miners kind of like concentrating a lot of power in a proof of work system, they can potentially become kind of like more vulnerable central points of failure, but also they can kind of like manipulate the power and manipulate transactions on their behalf and affect kind of like the end users. So there's some research that has been going on around the idea of selfish mining, the idea that miners might withhold some transactions to kind of like accrue higher fees, the idea of like obviously like a miner that concentrates a lot of power potentially creating a 51% attack, which is like reversing an existing transaction. And there's also very interesting research going on, and you have the link to the paper right there, this idea of like front-running transactions. So now that you have this like decentralized finance layer on top of like the base protocol, say in Ethereum, you can have miners choosing which transactions to include and to validate, and sort of like bet against them or front-run those transactions on like second layer contracts. So that's particularly problematic. So what we want to explore with this data set is, can we, like, beyond looking at simply like the number of miners in the system and how concentrating mining is, can we go beyond that and see if there's evidence that tells us that miners are colluding or that are connected or related in some like other unexpected ways? So basically what we will be working on is a data set that has on-chain transactions between Ethereum miners, and sort of like doing some basic analysis with that data set and looking how those miners can potentially be related. So if you're interested in the topic, I'd be happy, I mean, after we've done the notebook, I'd be happy to share some more information about like the research we're currently doing. So in the notebook, basically, we'll do like 4 things. First, we'll just explore the evolution of the Ethereum mining ecosystem. So just like look at the very basic kind of like data about Ethereum mining and how concentrating that mining is. Then we will sort of like pre-process some of the data in order to like build this graph object that's used in network X. Then we will we will visualize that graph, and then we will run some basic network analysis over the transaction graph. So again, we're going to be using Pandas, NumPy, NetworkX, Matplotlib, SciPy. It's just like system libraries. So yeah, hopefully, I mean, it's kind of long when you're going through it, but hopefully like the parts that you have to fill in, we'll go through like most of them as of now, and we'll just leave some out for you guys to like fill out on your own. So we're just gonna load the data frame that you have in the repo. We need to load libraries first. So here we have okay, so we're just loading the data. So we have a Pandas data frame. Basically, the data frame has snapshots of like 50 snapshots of activity in the Ethereum blockchain. So we've divided the, the activity over the last 4 years, or a little bit over 4.5 years, in slots of 170,000 blocks, which is roughly a month's worth of like mining. And we're currently looking at a total of like over 8 million blocks. So that's from the launch of Ethereum in mid 2015 to November 2019. So each of the, so we're creating a list that is this list that's called miner summaries, and each entry in that list is a data frame that basically, this is the data frame. The data frame has the miner address. It has the number of blocks that miner has mined up until that point. It has the number of transactions it has mined. So for example, in this case, we're looking at the 5th snapshot. So we're looking at the first 854,000 blocks, and we have the miner's public address, the number of blocks, etc. So the first thing we want to look at is, let's just simply look at the evolution of the aggregate number of miners and sort of like the transactions that they have sort of like validated with respect to the total miners. So we're just going to plot this graph, which shows us how many miners have been present at different stages in the evolution of the Ethereum blockchain, and how many transactions have they validated. Let me just run that block code, and we have, I'm just going to zoom out a little bit to show you this one in like one view. So we have, as you can see, there's almost like this logarithmic growth of miners. It has like particularly slowed down in the last few years, and you have like a very slow number of transactions mined that then like picks up and grows linearly. So from, again, each of these periods is like a month. So we have like 4 years worth of information here. So like for the first 2 years, there were like very few transactions that were being mined, but then that like quickly picked up and it has been growing linearly. And it makes sense that it has grown linearly because you have like a fixed limit of transactions you can fit in every block, right? So like if you're only, because you control so like the difficulty of your validating algorithm is sort of like set. You have a fixed number of blocks that you can produce, say, in a day, and for each block you have a fixed number of transactions that you can fit into. So it's roughly linear the way this grows over time. So the idea, what we want you guys to do is kind of like to plot a similar plot, but instead of looking at transactions, we want to look at blocks mined, right? So it's basically just, I mean, using the same code and changing, the miner summary, changing transactions for blocks. So this is kind of like the first question. So we're just going to run this block over here, and now we see. Actually, I'm going through like the solutions right now. I'm gonna, as we go along, delete some of the answers to some of the bonus questions because we want you guys to work on them. So maybe you'll be able to catch a glimpse of some of those. Maybe you'll miss them, but that's fine. And again, we're just looking now at the number of miners, and now we're looking at blocks instead of transactions. So you see that it has a linear relationship all the way from the start, while transactions doesn't. And kind of like the bonus questions, and we want you guys to think about that, is like, why does the number of transactions across time look different? The number of transactions validated, which belong to like those blocks, look different to like the number of blocks. Sorry, the number of transactions look different to the number of blocks that have validated. And here you can just change transactions mined. You can change it just like blocks mined. Okay. So that's the first part. So we can see that even though the number of miners has grown, it's growing a lot slower than the number of transactions in the network. So this is already telling us that there's a concentration of mining, right? That there's like, on average, the number of transactions and blocks that get mined by each miner has sort of like grown over time because miners haven't grown as fast as transactions and blocks have grown. So what we want to do?
Daniel,
Yeah.
can I ask a quick question?
Yeah, sure.
So the number of miners have grown logarithmically, but this is, I guess, it's not necessarily representative of the hash capacity, right? It's they could have gone like moved to ASICs and whatever as time went on. So this is just addresses of each miner, right? Like one miner is one address.
One miner is one address, but when you look at this data, the number of blocks mined by miner is a proxy of that miner's hashing capacity, right? Because like the more blocks you can mine, it sort of like tells you how much hashing power you control. So yeah, that's a good question, and that's relevant because we'll sort of like be looking at some of that later. So now we want to just look more specifically at who might be like the top miners. So we're just going to extract the addresses for the top 10 miners, and look at sort of like the evolution of those top 10 miners over time. So this is just a boilerplate code that's done for you. So we extract the addresses for those top 10 miners, and we're going to look at this sort of like stack plot that shows us the percentage of total blocks mined by miners that at the end of those 50 periods were in the top 10. So we basically took this data frame for like the last period, and then we looked at those miners and we looked at what share of the mined blocks they mined across the 50 periods. So this kind of like goes back to your question, and it shows us the relative power or the relative sort of like hashing capacity of those 10 miners across the history of the network. So something that's really interesting is that you can see that very quickly the network got centralized, and this is not the same for Bitcoin. It took a longer time for Bitcoin to centralize, but Ethereum very quickly got centralized, and you see that over a period of time, like over that, right after the 10th month after Ethereum was sort of like launched, you see that these 10 miners already controlled over 60% of the mining capacity in the network. So this is kind of interesting, and you can see how they have evolved. So we see that those top 10 miners have sort of like concentrated a lot, and kind of like the question we have for you guys here is we want to know which miner has lost most of like their share. So like by graphically looking, I would say it's maybe this one or maybe the green one that has like, it used to be pretty big and now it's a lot smaller. So what we want you guys to look at is sort of like understand that data set, that data structure, and see how that miner summary data structure is created, and just look at which one of these 10 miners has lost the most like kind of like mining share in those periods between like period 10 and period 50. So again, this is a small script that sort of like goes through that data set and gives you the again, I'm just gonna go and delete this one, and then it shows you the address of the miner who has lost the most. So you can see that the miner that ends in 98226, you can see it over here. You can see it over here. Oh, it's funny. But that's the miner that has lost the most, so like market share. And so let me just pull this over here. 226.
I think it's the third one, right?
Oh yeah, you're right. It's this one right here. Yeah. So this miner has been the one that has lost the most in that period of time. So we already looked at some kind of like online block explorers. So it'd be good for you guys to like get a hang of how those block explorers work by looking what's the name or what's the public name of that mining or miner or mining operation by going into that block explorer and looking this up. So you can work on that when you complete the notebook. So now what we're going to do is we're going to pre-process the data in order to define the graph. So if you remember when we were looking at sort of like the way in which a graph is defined, we have a graph is a collection of vertices, nodes, and a collection of edges. So what we're going to do is that we're going to create a directed weighted graph as follows. So every node in our graph will be a miner that has mined a block within our period of analysis. For every pair of nodes, for every like pair of miners, we will define an edge, which is the order tupled u comma v, if there has been at least one transaction from miner u to miner v. And we will assign every edge a weight that corresponds to the total value in US dollars that has been transacted from u to v. So remember when I told you that when you're creating a graph, you can either create like this multi-graph that has multiple edges between two nodes, or you can collapse those edges into like one single edge. So we're collapsing those edges, and the weight that we're going to assign to the edge between two nodes is going to be equivalent to the total value transacted between those two nodes. And why is the weight important? Because some of like the algorithms that we run to like calculate those graph properties have like weighted versions of them, right? So you can think about measuring things like degree distribution, and you can think of like weighted degree distribution. So weighted degree distribution is just like multiplying the number of like out degree or in degree by the sort of like the value of each one of the edges. So for example, in the case of transactions, you can measure the number of like transactions going out of one node, but you can also think of measuring the number of like money that has been going out of that specific node. So that's why we want to add weights into the edges. So what we are going to have is we're going to load basically sort of like two additional kind of like data sources. One is a slightly more complete data frame that has the same information that we had before, but it has some additional information. But it's basically the same: the miner, the number of blocks mined, the number of transactions, and that's the same like miner evolution kind of like list of data frames. But we're also loading another sort of like data source that's going to give us the transaction data. So before we do that, we just wanted you guys to create the list of nodes that we will be feeding into our graph object, our network X graph object. And given that each address is 20 bytes long, and we want to have a more kind of like nimble and small graph object, we want to change those node IDs for something that's simpler. So we're just going to use the index from this data frame to change the IDs from each miner from like their on-chain address to a smaller integer. So that's what we're asking you guys to do in this question, is just create that list of miners, not using their miner ID, but just using their address, but using their miner ID. Let's just go ahead and create that list of nodes. But we first need to pull this. Okay, here and here. And now for like each, now we have the sort of like list of nodes, but now we need the list of sort of like edges. So what we have is let me just pull this. Yeah, so we have another data set, which is the miners transaction data set, the miners transaction Python object. So let's look at what this object is. This is basically a list of it's a NumPy array, and the structure of this NumPy array, if you just want to explore it a little bit. So for example, look at the first entry here. So basically this NumPy array, what it has is it has the edges, meaning the transactions between two addresses. But the way in which that data has been stored is that basically we have a concatenation of the two on-chain addresses for each one of the nodes of the miners. So here you have one address, and here's the second address. Here is the value transacted, the aggregate value transacted over the 50 periods between those two nodes. And here's the number of transactions between those two nodes. So we just have an array that includes that information for all possible pairs. So again, because we're defining a directed graph, the order in which these two addresses are concatenated matters, right? So obviously, if we had this address going first, that would be a different sort of like edge that we'd be looking. So what we want to do, and that's already done for you in the boilerplate sort of like code, is we want to sort of like write that down in a different format, in particular in the format that can be used by the NetworkX library. So we want to have basically an order tuple where we have the ID of node U. So remember, instead of using the address, we're going to be using the miner ID. So the ID of the first node, the ID of the second node, and then a dictionary with a set of attributes. In this case, we're just going to use one attribute, which is the value transacted. This is actually the value in US dollars, so it's already converted for us. So there's a bunch of boilerplate code that sort of like does most of the heavy string manipulation for you guys. The only thing that we want you guys to create here is to create the edge sort of like list of tuples that will be feeding into the NetworkX API. So you can sort of like look at the manipulation that we're doing here, and you just need to like quickly like implement the way in which the edge of tuples is created. So now the way you use the NetworkX library is pretty simple. You define a graph object. And in particular, remember that we're using a directed graph. So we're using the digraph class. And we're going to add nodes to that graph by using the add nodes from method. And we input the list of nodes that we already sort of like defined up here. And we're going to add edges using the add edges from method. And we input the list of edges. So remember, the edges need to have this format. They need to be a tuple, which the two nodes, the two sort of like that order tuple, and then kind of like the dictionary of attributes. You can add an arbitrary amount of attributes to your edges. And if you wanted, you could also add attributes to your nodes. In this occasion, we're not sort of like adding attributes to our nodes. So we're going to go ahead and define our edges, and we're going to define our graph. So now we have our graph object, and that's very cool because now like all of the heavy work is done by the library when we want to calculate properties in that graph. So now something that we're going to do is we're going to visualize the graph. This is a drawing graph function that's sort of like underneath. There are a lot of like tools that allow you to like play with graphing network data. To be honest, I feel that sometimes those sort of like visualizations are very eye-catching, but they don't give you a lot of insights because there's like so much information in one visualization. So I'm a fan of like keeping it simple and like manually, having to like plot your data. So this is like underneath. This is using like the methods from NetworkX to draw networks, but that's basically just matplotlib. So you can manipulate, if you're familiar with matplotlib, like the visualization library for Python, you can sort of like manipulate some of the characteristics there. So this is already done for you. This is like that function that allows you to graph the data. But now what we're asking you guys to do is we will break up the graph by showing transactions with and between two groups of nodes. So in particular, what we want to graph is we want to look at the top 10 nodes and the rest of the nodes, the top 10 miners and the rest of the miners. So we just want you guys to define a list that extracts the top 10 miners. You can do that from the data frame that we have, the specific pandas data frame here. So we just remember that this is ordered in terms of like the number of blocks mined by Finage. But just looking at the top 10 here and the rest. So we just want you guys to extract those two lists and use those two lists in plotting the graph. So basically, you just have to fill this in because the rest of it it's done for you. So I'm not going to run this cell. I'm going to just only like show you guys the cell that has already run, because it takes a while to run. At least I have like a 2013 MacBook Pro. So this takes over like 5 minutes. Probably you have like newer computers, will take less. But here we can see that we're just sampling. We're not looking at all of the edges. We're just sampling a subset of the edges. But still, we can see how the activity plays out. We can see that there are a lot of transactions going out from the large miners into the smaller miners. So you can interpret that these are probably mining pools that are paying back to a bunch of like the smaller miners. You see that there are many transactions happening between the small miners, but still these arrows are pointing here. What's interesting is you see transactions happening from smaller miners into like the larger miners. So this is something that's interesting to think about and sort of like reflect on what that means. And obviously you also see transactions happening between big miners. So remember, again, here we have the big miners, here we have the small miners, and we're looking at transactions between them, between the two groups and within the groups. And we also have transactions happening between, within sort of like large miners. So again, is this representative of maybe some kind of collusion or alliances between larger miners? That's something that we can further explore and think about. So we have plotted the graph, and we show the top 10 miners on the left and the rest on the right. And finally, we just want to do some network analysis. So remember, we looked at the degree and what the degree means in the context of analyzing a network. Just move you back to our example here. It's a number of like edges that are moving either like in or out of a specific node. Because we have a directed graph, we can think of like the in degree and the out degree of the network. So we can just go ahead and use the built-in methods in the network X library, where we can just ask for the in degree of graph G by inputting the nodes. So you can look at the in degree for a subset of nodes. Here we're inputting all the nodes of the graph, and you can choose a weight. So again, the reason we're including a weight is because we, instead of looking at the number of transactions going into a node or the number of transactions going out to a node, we want to look into the number, we want to look into the amount of money going in or the amount of money going out. So that's why we're weighing a transaction by its value. So we just go ahead and run this cell in order to get the in degree and out degree. And again, this is a list that has the degrees for each one of the nodes in the network. So we're asking you to give us the average for the in degree and for the out degrees. So now when we run the average, this is the in degree average and this is the out degree average. So there is, oh, I think I erased the wrong question, but you'll get it in the I erased the question and left the answer, but we have a bonus question there asking you guys, why is this the case? Why is the mean out degree equal to the mean in degree? So just you have to think through that a bit in terms of sort of like understand what that means when you're looking at all of the nodes within the network. Now we're going to look at the density. So the density of a graph is, remember, when we're looking at connectedness, we wanted to see like for a given graph, what percentage of potential like possible connections between nodes existed. So let me just go ahead and run this, and we have the density for the graph is 0.0002. And we want you guys to think of like how to interpret this. So I'm just going to go quickly and erase the answer in case you read it. You're lucky. And what does it mean to have that density? So again, we're just using functions that are built into our sort of like network X library. But you don't have to do these. These are already sort of like built in for you. You just have to like answer the interpretation. And finally, we want to look at the strongly connected components. So remember that normally no, I mean, normally, especially when you look at like real life networks, and in particular, when you look at transaction data, what you will have is like a large connected component and a lot of like smaller connected components. So what we're going to do is we're going to run this function from the network-X library that tells us that gives us the strongly connected components for a graph. So remember, when we have a directed graph, the strongly connected components in a directed graph are sort of like the subset of nodes where each node in that subset can be reached by any other node by sort of like traversing the arrows or the edges in the directions in which they are defined. And we want to sort of like look at the strongly connected components in that graph G. And we're asking you what percentage of the nodes in the graph are in the largest strongly connected component. So looking at strongly connected components, it's a very sort of like important way to sort of like analyze the core topology of the network, because it gives you like those subsets or those clusters that have tightly knit relationships. So again, because we're looking at minor transactions and because we want to understand how closely related some minors might be, looking at the different like strongly connected components can give us some insight as to like which are the clusters of like highly connected minors. So I'm just going to go ahead and run this cell here, and we have basically this function is giving us a list of strongly connected components. So we have, and if you want, we can just print that out. Let me just print this part of that out. Oh, sorry, we have. Let me see if this works. It should work. Okay. Oh, okay. I don't know what I have wrong there, but basically we have. Oh, so this is. Yeah, this is.
Daniel, the generator might have been already consumed.
Yeah. You're right. Let's just do this. So yeah, this is not ordered, but you see that. Sorry. So you see that if we make this a little bit larger, you already see that you have some components have 3 nodes, some other components have 5 nodes, etc. So we're asking you how many nodes are in the largest one of those components, right? So I mean, the answer is right there. And actually, if you run that part, that cell, you have that less than 0.2% of the nodes are in the largest strongly connected component. So the largest strongly connected component is very small, but what would be interesting to look at is how much hashing capacity does that component control, and how strongly connected is it, how many transactions and value has been sort of like transacted between those nodes. So that's it for the homework and demo and workshop. You have the data in the repo if you want to play a little bit more with it. Kind of like this idea and this exploration of how do different sort of like stakeholders, and in particular validators and infrastructure providers interact in blockchain networks is something that me and some other people in the iSchool are really interested in. We're actually working under grant from Ripple sort of like to explore some of these issues. So if you're interested in sort of like further exploring this, or just like doing data analysis with blockchain data in general, just hit me an email. I'm sure like Simon can share my email with you guys. And thanks for joining. And have a good one. Stay safe.
Yeah, thank you, Daniel.
Thank you, Daniel.
Thank you.